Okay, I will record this lecture into two parts. In the first one, I will discuss some of the remaining articles from the chapter, and in the second portion, we will do some problems, and that will also serve as the tutorial of the week. Okay, so let's start from where from where we left in the last class. Um, in the last time, we were discussing about how to describe a wave. And we discussed that to completely describe a wave on a string, that is the motion of any element along the length, we need a function that gives the shape of the wave. Um, and I write the function which can describe the shape of the wave as, so this is the distance element, this is some function h whose arguments are x and t, and x is simply in position and t is for time. So basically, this is a function which can give us the shape. Now we have to figure out what is the formal form of this function. So remember, this is the transverse displacement. So since we are talking about a wave on a string, so basically it's a transverse wave. So we need a function which can describe these crusts and these troughs. So basically, the y is along this direction. This is the transverse or perpendicular distance of the wave. So uh, just overlook all the mathematical technicalities, since we do not need all those things in the course. Um, in the last chapter, we discussed that we can describe a wave by a sinusoidal function, since this is a sinusoidal shape. So it's a periodic one. So either I can describe it with a sine form or with a cosine form. So now we have technically two types of solutions of this wave. So both functions can describe the shape of the wave. So either it will be y of m sine kx minus omega t, or y of xt is equal to ym cos kx minus omega t. So in this equation, y is transverse displacement, x is position, it can be any position, t is time, ym amplitude, or the maximum transverse position. Omega is angular frequency, and k is angular wave number. This is also called as spatial frequency, and this one is also called as temporal frequency. So remember, the word temporal is for time and spatial is for x coordinates, position coordinates, not necessarily x. So this is temporal frequency. There are many types of frequencies in physics. So in the same fashion, we define angular frequency or the temporal frequency, that is number of waves per unit time. Similarly, we can define this angular wave number or spatial frequency k in a fashion that number of waves per unit distance. It's 2 pi by lambda. So, so this capital T denotes the time period of the wave, and this lambda denotes the complete wavelength of the wave. So these are just mere definitions, nothing else. So basically, I should write this here, um, to complete the sense. Number of waves per unit time. So this is number of waves per unit distance. So these are just two definitions. I'll share a resource with you which will serve as a purpose to understand the idea of frequency. And there will be a lot of frequencies mentioned in the resource that we often use in physics in different branches. But at the moment, we only need to differentiate between f, omega, and k. So all of these are three different quantities. F is a linear frequency which is measured in hertz, and while so this is an angular frequency in the units of radian per second, or and this is in this angular wave number is in radian per meter. So now from this definition, we can calculate the formulas. So let's see how we can come up, how we can derive these formulas. So first discuss about amplitude and phase. So we know that amplitude is the maximum displacement, maximum transverse displacement of a wave, which we are calling as Ym. So since it's just the maximum value of distance, so it is always a positive quantity. So if I put a negative sign with Ym, it just means that the direction is reversed, but its magnitude can't be negative. In generic sense, magnitude should always be positive. So negative sign will only denote that this is directed towards the negative coordinate system, the negative axis. Um, and the argumentative sign that we are dealing with kx minus omega t, this is called the phase. So this is the phase of the wave. So and since so I can also call it as theta. So if x and t are changes, it means the whole of the theta will change. But the value of theta will be from -1 to +1. Since it's the argument of a trigonometric function, and the range of a trigonometric function will be from -1 to +1. So whatever the value of x and t we are taking here, theta can't be greater than +1 or can't be less than -1. So we can see that phase is changing linearly with time because all of the terms including in this relation are of the power 1. So at the extreme positive position, theta will be +1, and extreme negative value, theta will be correspondingly the negative axis. Okay, but keep one thing in mind, that whenever you try to round off numbers, you must be cautious rounding numbers in theta, because if you round a number, say 50.13 degrees to 50 degrees, that will cause a very big mistakes in your calculation. So you have to be cautious while doing rounding of numbers. So it's a little bit considerate. So now calculate wavelength and wave number. So how we can relate wavelength and wave number. Okay. So let me define wavelength first. So suppose a wave on a string is produced like this, and after this point, this wave is gonna repeat itself. So the distance between the initial point and the point after which wave will start repeating itself is called wavelength or lambda. and this quantity will always be parallel to the direction of propagation. So the equation of motion for a wave is y is equal to ym sine kx minus omega t. So at t is equal to 0. So remember, this is the function of x and t. So I can write this as sorry, y x of t. So I can write this as yx0 ym sine of kx. Uh, Also, after covering a distance of 1 lambda, wave will be at its initial position because the function is periodic. So it means I can say that the function will remain same if I write this as sine k into x plus lambda. So if I add lambda to our function at position or 2 lambda or 3 lambda or n lambda, the shape of the wave will not change because it's a periodic function and we are completing one oscillation. So I can equate both of these equations, or I can also write this as so this won't be any there won't be any change if I'm gonna write this equation as sine kx plus 2 pi, because this is a complete oscillation after which wave is gonna repeat itself. So let's compare equation number one and equation number two. So let me do this over here so we can finish this on the same slide. So this will be kx plus 2 pi. So if I'm going to compare this term will cancel with this term. Sine will be cancelled with this sine, and uh, these are just going to be cancel out in comparison. So kx plus lambda equals k into x plus lambda. So kx plus 2 pi equals kx plus k lambda. So this is going to be cancelled with this quantity, and we can figure out that k equals 2 pi by lambda. This is our earlier definition of wave number that I just posed a moments ago. So this is angular wave number. So if you are measuring angle in radians, then the unit will be radian per meter. Otherwise, it will just be inverse meter. So either the unit can be radian per meter or it will just be per meter. It depends what you are in what units you are calculating um, phase. So similarly, we can also define the relationship between angular frequency and frequency. Although we did almost of the same calculation in chapter number 15, but let's do it again for the sake of completeness. So relation between angular frequency and frequency. So let me draw this wave again over here. So this is my wave, and my wave equation is y of m sine of kx minus omega t. So now I'm gonna put x is equal to 0 because I have to calculate time. So this is my other condition. So now this will be y of 0t, y sub m sine of minus omega t. Since after this, so this is lambda, and after time capital T, if it starts from t is equal to 0, so then at time small t is equal to capital T, wave will reach its initial position, and the total phase that it will cover during this journey will be 2 pi. So I can write the same equation as y of m sine minus omega t plus 2 pi. So let me call this equation number 1. And similarly, I can also say that after completing one vibration, the time will be equals to time period capital T, and wave will reach back to its initial position, or the same position from where it starts, since the sine is a periodic function. So y sub m into sine of minus omega t plus t. So it doesn't matter what multiple of t I'm gonna add. So if I'm gonna add t plus n pi as far as n is an integer, so 0, 1, 2, 3, it doesn't make any difference because it's just a number of oscillations, number of complete oscillations of a wave. So let's again compare both of these values, both of these equations. Comparison yields. I know you can simplify it on your own. So negative signs will be cancelled out. Y m sine y of 0 t will be cancelled out. And you will just be left with this equation. Minus omega t plus 2 pi minus omega t. I think I should write this as so this negative sign will come out here, and similarly that negative sign will come out of here. So basically this thing, so I should make a change over here, and the negative sign will be like, uh, so here I have a negative sign because I'm gonna bringing out this negative sign from the argument. So let me put this negative sign over here rather than into the argument. So otherwise, you just have to figure out what the phase will be. So in that case, the phase would be minus 2 pi because our initial argument is minus omega t. So to get rid of that extra negative sign, I, I, I brought out the negative sign out of the argument. So now the equation will become uh, linear with a positive sign. So this will just be omega t plus 2 pi, omega t plus omega t. So this will be cancelled with this, and you will get t is equal to 2 pi by omega, or omega is equal to 2 pi by t. It also equals to 2 pi f. Okay. So since my earlier argument might be confusing, so let me elaborate this again here. So initially I have wrote sine of minus omega t. So remember, this negative sign is not with uh, this omega t. This is whatever the argument of sine is. So either I can write this as sine of omega t, or if I'm gonna write this, so then I have to put minus into omega t plus 2 pi, because this negative sign is with the argument of sine, not with omega t. Since frequency can't be negative and t can't be negative, but the argument of sine is negative. So this is what I'm trying to do here. So either you can do this way, or uh, you can just put the negative sign out of the argument. So both are equivalent statements. See. Okay. Uh, so let's write a more general form of the equation. Um, our wave equation is y equals y sub n sine of kx minus omega t. So this is for a wave which is traveling towards right. So this is the speed of the wave, and it is starting from this point A, where phi is equal to 0. So but if my wave is starting from this position, so let me call this. So if my wave is going to start with this position, it means now my phi at this point B is pi. Or what if my wave is going to start from this position? So say So let me call this point C, and my phi here is either minus pi by 2 or 3 pi by 2. So it means I need to add a phase constant in my original equation. And that phase constant can be positive, can be negative, it depends upon the direction of the wave. So in general, so since if I assume a wave is traveling towards right, then I'll just have to add a phase constant with a plus phi. Sorry for the background noise. Okay. So this is my wave equation. But if a wave is traveling towards either towards left or towards right, and phase is positive or negative, we have no information what could be the phase. So the most general form of this equation can be sine of kx plus minus omega t plus minus phi. So this is the most general form of the equation. Or for the sake of simplicity, since this phi is just a constant, so you can just put a plus sign here. So even if phi is negative, then minus pi by 2 will automatically change its positive with the negative sign. So this is the most general form of the wave equation that we can deal in this chapter. So most general form of the wave equation. Okay. So now in this equation, so let me call this equation number one. You might be surprised that kx term is with a positive sign, while omega t term is with a negative sign. With a positive sign, and this is with a negative sign. So why I can't just switch the signs? So for example, can I write or an argument like this minus kx plus omega t, at least in this, for the wave which is traveling towards right. For a wave traveling towards right, and let me be more specific, that is towards positive x direction. So the answer is no. Now we'll fix. So basically, this notation is coming from another idea, that what would be the direction of the traveling wave. So if a wave is traveling towards right, then it means it is traveling towards positive x direction, and by convention, the velocity will be positive because it is accelerating towards positive x-axis. So basically, that thing uh, will allow us to figure out the sign with the omega t factor, and we will and let's see how this relation depicts that velocity will be positive. Or what if I put a plus sign here? Then it will clearly be meant that wave is traveling towards negative direction. Okay. So now we are gonna figure out the speed of a traveling wave. The speed of a traveling wave. So since a wave is gonna repeat itself after a certain interval of time, so which means or we can also say that, so if the shape of a wave is like this, um, if this is the shape of the wave, and this point A. So basically, it means that this point is gone. This point is not shifting towards any other point. This is a fixed point. So this won't change itself. So what is gonna change here? The position of the particles of the string are gonna change. So basically, wave points are not being changed. Points on the string do not retain their displacement, but the points on the waveform do. So these are the points on the waveform. So this is the shape of the wave, and all the points which are making this wave were said to be the points on the waveform. So this is a very, very important idea that we're gonna use here. So remember, so this is a waveform. So points on the waveform do not displace. So because they are the structure of the wave, they are defining the structure of the space. But points on the string displace. They do not retain their position. They do not retain their position. So what this means? It means that the function that I have written earlier, y equals y sub m sine of kx minus omega t, this phase is defining the shape of the wave. So basically it's a representation of the points on the waveform, not the points on the string which is going to displace. So it means, so this function will remain constant. So it means in what direction, whatever the velocity of the wave is, uh, so this function will not gonna be changed. So that this will remain constant. So I can safely assume that this argument is a constant factor. So kx minus omega t equals constant. Even you can also check this thing. So for a fixed x in t, the phase will always remain fixed, no matter what the speed of the wave is. So, if you fix your x and t, no matter what the speed of the wave, what is the direction of the wave, this function won't be changed because k is a number, x is a number, omega is a number, t is a number. So all numbers will make up just another number, which is a constant quantity. So that's another way to visualize this thing. So let's differentiate this. Um, so I'm taking differential. So let me call this constant alpha. So since this is a constant, this is 0. And I can write this k of x, d of kx minus d of omega t. K is a number, so I can bring this out. Omega is a number, so I can also bring this out because these are not functions. So we can take the derivative of the function. Omega dt is equal to 0. Let's divide by t. Dx by dt minus omega dt over dt is equal to 0. So kv minus omega is equal to 0. So v equals omega over k. Omega is a positive number, k is a positive number, so which means that v is also a positive number. So for a wave which is traveling towards positive direction, will have a positive velocity. So this is a way to define the velocity of a wave, the velocity of a traveling wave. Now we know that omega equals 2 pi f and k is 2 pi by lambda. So this 2 pi will be cancelled with this 2 pi and you will get the very famous relation v is equal to f lambda. So this is how we can derive this relation. So, uh, so this equation represents the speed of the traveling wave. So basically, this is the most general form of this equation. So equation one is the general form of the equation, while equation two is not. It's not a very. Uh, it's not a very say does not depict the more technical picture of the situation. So you can see that if I put a negative sign here, I'll get a positive v. So but what if I start from this argument kx plus omega t equals alpha. So just take its derivative again, differentiate it with respect to t. So this will be k dx over dt plus omega is equal to 0. So k v plus omega is equal to 0 and v will be minus omega over k. So you can see that this negative sign is means that wave is traveling towards left direction. So left is just a convention. It means wave is traveling towards the negative x-axis. Similarly, you will get a negative sign in this relation too, or you will not think this. So this is the speed of the traveling wave. So this is it from the lecture section. Now I will do some of the problems and upload those in a separate video. So link will be shared in the Google Classroom. Okay. Thank you.